Okay.
Okay. Good. Then, yeah, thanks again for inviting me. And I'm going to talk about causal inference today, particular project inspired by our work in COVID, but I'll talk about some more general points about causation. This is joint work with Matteo Bonvini, he's a graduate student at CMU, and my colleagues Ed Kennedy and Valerie Ventura. So I'll just give you a little bit of background about how I got involved in this particular problem. Then I want to talk a little bit about the different types of models we're talking about, and in particular, it's the relationship between epidemic models and causal models that really want to focus on. Then I'll give you some results for this project and talk about sensitivity analysis. So just some background. I'm going to be talking about the causal effect of social mobility on COVID-19. The way I got involved in this is I'm a member of Delphi, which is a epidemic modeling group at CMU. That's our website if you are interested. And this group was formed to do epidemiological forecasting. The eventual goal is to make epidemiological forecasting just like weather forecasting. And it was started by my colleagues, Roni Rosenfeld and Brian Tibshirani, in about 10 years ago. Now, as you might expect, we typically do flu prediction, but when the COVID-19 pandemic hit, for obvious reasons, we switched over to COVID prediction. But what I'm going to talk about is not the efforts of the main group, so that it's a very large group. I think there's about 60 people. And most of the resources are devoted to predicting COVID and measuring other things about it. This is a bit different because in this particular project, we're interested in predicting the effect of a hypothetical intervention. An intervention here, I mean a lockdown, school closing, masks, things like that. And we're not going to focus on the whole problem. You can think about it as some intervention occurs, and many of these interventions would affect social mobility. And then social mobility would affect some outcome, like hospitalizations or deaths. And so the whole causal question would involve this whole pathway. We're only going to focus on a sub-question, namely the relationship between mobility and the outcome of interest. And so this will be causal inference meets epidemics. Let's state the problem, and we'll keep it simple for now. So we're just going to have a single state, one state in the United States. And we have a time series with two variables. The variable A is going to be some intervention. And for this talk, it'll be mobility. Actually, it's going to be the opposite of mobility because it's going to be what fraction of people stay home most of the day. So it's really anti-mobility. And that's measured at t times. And then the other thing is the outcome of interest, which in our case will be deaths due to COVID. So we just have this bivariate time series. And here's what they look like. So what I'm showing you is just log deaths for the first 40 some odd weeks in the pandemic. Again, on the log scale, and this is just the 4 biggest states in the United States: so New York, Florida, Texas, and California. And this staying at home variable or anti-mobility, this is what it looked like. It started out around 25%. Apparently, there's quite a few people, fraction of people just normally stay home most of the day. And then as the pandemic started, of course, there was the lockdowns and the proportion staying home doubled. And then this gradually went down throughout the pandemic. So the problem we're interested in is, given, let's think about those time series of anti-mobility. And by the way, here's a notation I'll use throughout the talk. When I put a bar on something, it does not mean average, it just means the past. So it means all the measurements up to time t. And so we have that for A and T. And what we want to ask, though, is besides the observed mobility pattern in a given state or a given country, let's consider a different pattern. So let little a here be a particular set of values of mobility, different than the one that we actually observed. And we want to ask the counterfactual question, what would the number of deaths at time t have been had we could have set the actual mobility pattern to this particular hypothesized mobility pattern? So we might have asked, what if everybody had stayed home? Or what if nobody had stayed home? And so to answer those kinds of questions, it's very useful to introduce potential outcomes, also called counterfactuals. These are new random variables, y sub t with the bracket a here. This is different than these observed things here. This is what yt would have been if I had set capital A equal to this particular small a. So this is something that hasn't happened and we didn't observe. So that's called a potential outcome or counterfactual. So just to be clear, there's the observed variables, the A1, Y1, A2, Y2. And the time periods we're going to be dealing with here are weeks, by the way. But then there's these counterfactual random variables. There's infinitely many of them. For every hypothetical setting of the variables A, we have a new counterfactual, which is what yt would have been if we had fixed it at this pattern. So we have a large number of random variables, only a small number of which are actually observed. These are the observed, and these are the counterfactuals. What we're interested in is estimating the mean of this counterfactual random variable. So we saw, let's say in New York, how many deaths there were at a particular time, and we want to ask, what would the deaths have been if we had a different mobility pattern? So this is a classic causal question. And for now, I'm going to assume, by the way, there's no other variables. I mean, you could imagine there should be other variables involved, but let's just concentrate on the A's and the Y's. So how do we get this thing? Well, here we're going to use what's called Robbins' G formula. This is a theorem that Jamie Robbins proved in 1986, which says that under some technical conditions, and in particular, assuming no unmeasured confounding, the mean that y would have had if we had observed a different set of A's is given by this formula. This will be very familiar for people who do causal inference, but I'm assuming probably most people don't do causal inference. And so the formula looks a little bit complicated. It's what it is. It's just this mu thing is just the mean of the number of deaths given the past. So this is the usual regression function. And then you take that function and you average it over all of the Y's, but not the A's. So again, if this is not equal to something you're familiar with, it's not a marginal distribution, and it's not a conditional distribution. It's just some function of the joint distribution. And this can be proved to be the correct thing to compute, but just think of it as a complicated functional of the joint distribution P. Again, it's known as the G formula. Or later on, Judea Pearl worked a lot on causality. He called this the backdoor formula. So I don't have time to go into the details of that formula, but let me just say it is a theorem originally from Robbins, 86. Here's a quick 5-second intuitive description of where it came. It's actually a theorem, but I'm just going to give you a heuristic, which is if you imagine writing down the joint distribution, so you have a density for A1, a density for Y1 given the past, a density for A2 given the past, so on. And if you take that joint density and remove all the distributions for A is, again, the mobility, just remove those densities and replace them with point masses at a particular value. So that's not conditioning. That's defining a new joint distribution where we have a point mass for A1 and a point mass for A2, and all the rest of the distribution is left alone. And now that's a new joint distribution, and you can ask, what's the mean of YT in that new distribution? And it's exactly the G formula. So we would get exactly this formula. Anyway, the bottom line is we do have a formula for computing the causal effect, but of course it involves in all kinds of things about the joint density that we have to estimate. Now, so let me just go back. Estimating this formula is a non-trivial thing. A natural thing to do is for these distributions P is we would put in models for those distributions. And a common way to specify models, especially, and this is where the epidemic stuff comes in, is to use what we call sequentially parametric models, which just means you have a model for a time series, which is expressed as a distribution for each time t given the past. So it would look like this. We have a model maybe for A1 here, which depends on some parameters. Then we have a model for Y1 given the past. Then we have a model for Y2 given the past, and so on. And so it's a very natural way to specify a model. But as we're going to see, this actually causes some problems. And the problem intuitively is this. We put these parameters in here so that we can estimate this distribution. It's very hard to estimate a single time series non-parametrically because there's a curse of dimensionality. As time goes on, you're conditioning on more and more features. And so the dimension explodes. So we're going to have to use some sort of model. And that involves putting parameters in here. But these parameters, whatever we're using to parameterize the distribution, they're not really what's of interest. Ultimately, what I care about is that G formula. So I could take this joint distribution here, estimate the parameters, and stick it into that G formula. Effectively, what I'm doing is I'm estimating some function of all of these thetas. So there's a large number of parameters now, but the causal effect is ultimately some function of those thetas. Of course, you could look at other functions of the thetas too. So for example, I could ask you not a causal question, but a prediction question. What is the distribution of YT given the past? How dependent, how much dependence is there between, say, YT and the past variables? So imagine there's many different ways you could make that formal, but ultimately that would define another parameter, K of theta. So you could imagine you have all these parameters in here. The causal thing you're interested in is some nonlinear function of all of the thetas. The more familiar things like prediction and conditional independence, they would be a different function of the thetas. And the problem here is that those two things, let's say we have some conditional independence parameter, kappa of theta. That kappa and psi are not going to be variation independent. That is, I cannot vary kappa without forcing myself to vary psi and vice versa. They're not separate parameters. Because we didn't express the model in terms of these things, we expressed them in terms of these more primitive sequential parameters. And this causes a big problem because when you fit the model, you typically use regression or maximum likelihood or Bayesian inference. What you're effectively doing there is really fitting the conditional independence parameter kappa. So what's going to happen is if there is conditional dependence, you're going to get a value of kappa. You're going to get something which measures conditional dependence is going to be not zero. And that's going to force the causal parameter to be not zero because they're not variation independent, even when there is no causal effect. So what this effectively means is when you specify a parametric model sequentially, you are actually guaranteed to reject the null hypothesis that there's no causal effect, even when there is no effect. This is called the G-null paradox. It's because it sounds very counterintuitive. Here's some references for the G-null paradox. Just to give you a little bit more intuition on what's going on here is the problem is that we're going to get dependence even when there's no causal effect due to variables that we call phantoms. A phantom is an unobserved variable. It's a latent variable, but it's not it affects the covariates or the outcome, but it does not affect treatment. Okay, so some sort of baseline health thing, for example, might be a phantom. The important thing is when we're doing causal inference, we're always worried about confounding variables. These are variables that affect the outcome and the treatment. If you have unobserved confounding variables, then you can't really estimate the causal effect. But these variables U are not confounding variables. They don't affect the treatment. they only affect the outcome or the outcome in any covariates, but they don't affect treatment. So these variables, in some sense, are harmless. They don't change the formula for the causal effect. You don't need to observe these latent U's in order to be able to estimate the causal effect. So it sounds like they're harmless. But the problem is, when combined with a sequentially specified model, they create a big problem. So let me just make this really clear by showing you a simple example. Suppose we had a treatment at time 0, call it A0. Then I observe some other variable, anything, x. Then I give you another treatment, time 1, say A1, and now I observe an outcome y. And let's consider an example of a sequentially specified model. So how would you model y given the past? Well, the simplest parametric model might be that the mean of y given the past is a linear model. So there you can see the linear effect. Now, the distribution for A1, the A's is not so important here, but the distribution for x given the past, let's say x is binary. What models do we have? Well, a common model for binary would be a logistic regression. So that would mean that the mean of y given A0 has this logistic form. So this is just an example of a sequentially specified model. People do graphical modeling. This is how we specify almost all graphical models, for example, is everything given its parents. If we now do that G formula, you just plug it into that integral, and here's what the causal effect is. This is the mean that y would have if we set the treatment to be little a0, little a1 is given by this formula. And that just comes from some algebra. The form of this is not so important. But now if you ask me what is going to happen if a0 is a certain value or a1, I can just plug it in here. So that's everything that I need. Okay. There's a bunch of parameters in here. There's betas and gammas and so on. Okay. But now let's ask, suppose there's no causal effect. Suppose it turned out that a0 didn't affect y and a1 didn't affect y. That would mean that this function psi shouldn't depend on a. So that would mean that psi of a0, a1 better not depend on any of the a's. And you're probably thinking, oh, I'll just set these betas equal to 0, right? If I set the betas and the gammas equal to 0, for example, then the psi won't depend on a anymore. The problem is you can't do that because, let me now show you the next graph. I've added in a phantom variable that affects x and y. Let's look at the second graph, actually. So we have our a's and x and y, but now we have this phantom, which we don't observe, which affects x and y. And again, it can be proved that the causal effect is still estimable, and it's still given by the same formula. So in principle, we don't need to know u anyway. But if you're familiar with directed graphs, you'll now look and see that x is what's called a collider. It has an arrow pointing in two different directions. There's two arrows colliding at x. And for those who know directed graphs, what that tells you is y is conditionally independent, for example, on a1 given x and a0. In other words, y is dependent on the a's, marginally and conditionally. So, and if you're not familiar with directed graphs, well, it just turns out there's a simple way to look at these graphs and figure out what's independent of what. So the fact I just said can be checked easily. So to summarize, the situation is this. There's no arrow from a1 to y or a0 to y. So there's no causal effect. But y, if you did a regression, you would see y is dependent on the past. And that means if y is depending on the past, when you do maximum likelihood or least squares, whatever, these beta hats and gamma hats are going to be non-zero. And if they're non-zero, this causal parameter is now going to depend on a0 and a1. And you're going to falsely conclude that there's a causal effect. So the presence of the phantom implies that maximum likelihood and Bayesian inference will give you non-zero parameters, and that forces the causal effect, the formula for the causal effect, to depend on A, which means you would reject the null hypothesis. So this is a very strange, unsettling fact, if you've never seen it before. And And what are the solutions? One solution would be to not use parametric models, but use non-parametric models where the problem disappears. But again, when we have a long time series, that's not feasible anymore because the parameters grow and you get as time goes on, and you get a cursive dimensionality. So one way to deal with this is simply to take that G formula, which is now, again, it's some long complicated integral. If I plug in my sequentially specified model and do the integral, I'm going to get some complicated nonlinear function of treatment and beta. And now what you do is, and this is, you can think of this as being equivalent to now specifying a model for the treatment effect. You've effectively got a formula for the treatment effect that involves a bunch of parameters beta. And such a model is usually called a marginal structural model. It's a model for the causal effect. Okay, and I mean, a simple marginal structural model would look like this. The causal effect as a function of A only would be maybe some linear model in terms of A. But we're not specifying such a thing. We're computing it. We're going to take that sequentially specified model, put it into the G formula, get that formula, and now we're going to concentrate directly on estimating that formula rather than doing maximum likelihood. So again, this would not be a generative model. You can think of this as a semi-parametric model for the causal effect. So the general strategy we use is you start with an epidemic model. I'm going to start with one in a minute. You do the G formula, which is some big integral. That gives you a formula for the causal effect. Now you abandon the model and directly estimate beta using this formula, instead of maximum likelihood or Bayesian inference, we use something called an estimating equation. And this avoids this phantom bias. Okay, so let me skip that actually. So the plan is we're going to start with an epidemic model, do the G formula, but then we're going to estimate the G formula directly. We're not going to go back and estimate the epidemic model. And there's a million epidemic models, and I'm just going to talk about one example model. In fact, you know what? I'll just give you an example like this. This is called a semi-mechanistic model. This is an example of many, many different types of epidemic models. This one says that the expected number of infections, so IT is the number of new infections at time t, is some linear combination of past infections, and you can see the I here is past infections. Pi measures if I get infected at time s, how many people will I have infect by time t, at time t? And then there's a term here, which is just capturing the intervention. So if beta was 0, that would disappear. And then we don't really observe infections. We typically observe deaths or hospitalizations. So that would be the variable y, and we would say an example of a model is that mean of y given the past is some linear combination, again, of infections, and then there's some function here, g, which is just saying essentially if somebody gets infected, at a certain of a certain fraction of people who are infected, what fraction died at a later time. So this is just an example of an epidemic model, but I wanted you to see that this is a very natural model and it's been used successfully. And it's exactly of the form I just talked about, though. It is a sequentially specified model. So people are using this model, but they haven't recognized that it has this G-null paradox. You're going to reject the null that beta is equal to 0, even when there's no causal effect. Okay. And by the way, I'm not going to write out what the G formula is for this model. It's quite complicated. We have actually a separate paper about that. But the point is, it is something you can compute. But what we decided to do, at least this paper I'm talking about, was we look at that model and we're just going to change it a bit. We're going to both make it less complicated and more complicated. So after looking at these models, we decided on the following model. The treatment process, AT, given the past, is something I'll describe later. That's not so crucial here. But it's that the fact that infections for COVID, we found it was pretty good approximation really to only go back 1 week. So we're going to say the number of infections at T is some multiplier of infection. how many people got infected last week. It's not exactly true, but it's a pretty good approximation. But then we multiplied here by these e to this thing. And what the CT is a non-parametric model of the epidemic. What I mean is that if there was no treatment at all, e to the CT would be a standard kind of epidemic model. And this gamma of AT is a function of the treatment. So this is how we're putting the treatment in. And then the YT is just like I mentioned before. It's a linear combination of past deaths. So it's very similar to that semi-mechanistic model. Keep in mind that IT is unobserved. Okay. This FST that was in the equation is, again, how many people die from somebody infected at time S. We actually broke this up into two pieces, which is DS, which is what fraction of people actually die at all from COVID. And then given that you die, how long does it take you to die? So D of S is the probability of eventually dying. This part of the model, we actually did not estimate ourselves. We took this out of some other literature. So this turned out to be in some paper in Nature, I think, they show that this can be modeled fairly accurately as a sum of two gamma random variables. So we're taking that as given. Now again, we could apply the G formula and directly, and we can here because it's a pretty simple model. And let me just jump actually. So some nice things happen. Even though the infections were in the model, when you do the G formula, they drop out of the model, which is very good since we don't observe them. What ends up happening, though, is simply that psi, the number of people who die, is some now parametric function of the treatment, past treatment, and a bunch of parameters. I'm just going to summarize this for you. Let me just summarize it for you. We tried different models for how the treatment comes into it, and it turns out linear fits really, really well. So that was easy. Remember, I mentioned there's a component of this model which is sort of the non-parametric part, or flexible parametric part, I should probably call it, which is meant to capture the shape of the epidemic on the log scale without treatment. We just took that to be a sum of orthogonal polynomials. So that's just a convenient choice. I'll skip that point. It turns out that again, I'm skipping some steps here, but this turns out essentially to say the log number of deaths. And remember, this is this is the log number of deaths, LT, log number of deaths. The mean of that is approximately beta times M, where M is no longer the treatment A, it's actually the cumulative treatment. So it turns out, this comes from just doing some calculations with this model, that you end up with the cumulative amount of social mobility. So the bottom line is, starting with a simple epidemic model, doing a few simplifications, we get that the mean of the log number of deaths is beta times the cumulative A's plus a polynomial. You might wonder, where are the other variables? Where are all the past Wasserman? But remember, this is after doing the G formula. This is not a model for the epidemic process. This is if I took the model for the epidemic process, crank it through the G formula, this is basically the formula I get. It's only a function of A. The K has to be chosen carefully, the number of terms. We used AIC to do that, but of course, there's many different ways of choosing the complexity of a model. And that turned out to be pretty important. If you don't choose B, we just, our first guess was just to pick an arbitrary number of terms in this piece and make it the same as every state, and we got very strange biases. And then we finally realized we had to choose K more carefully. So let me just back up for a second. In case I've confused anybody, let me just say that the main point here is that our model for this counterfactual, what would have happened if we'd set mobility equal to a particular vector, little a. There's a formula for it, which is beta times the sum of those a's and a sum of polynomials. We're going to now estimate all the betas in here. And now, once we do that, I can tell you give you these counterfactual predictions. I can put in a beta hat here, and then I have a curve for what the outcome would look like. So I can put in various hypothetical, once I do the estimation, we can start asking these hypothetical counterfactual questions. I can say, okay, what does the model say about what if everybody had stayed home? What if nobody had stayed home? What if people had stayed home for 5 weeks and then started going back to work? You can ask all these hypothetical questions. So I'm going to show you, when I finish fitting the model here, 3 hypothetical scenarios. One of them is called start 1 week early, which means we take the observed mobility pattern for one state and shift it a week earlier. So we start at A2, A3, and A4. And so that shows you what the effect on that state would have been if they had started shutting down a week earlier. And we also did 2 weeks earlier. Another thing we're interested in is we know that all the states, people stayed home more and more and more, and then it died off. And so we can ask, what if they had stayed vigilant? Which means the way we're going to investigate that is, what if it had gone up, but when it came down, what if we had reduced the slope by half? So it died off twice as slowly. So this defines 3 different hypothetical kind of interventions that we can now say, we can estimate what would have happened under those interventions once we estimate beta. So as I said, we don't want to use maximum likelihood on that model, and we don't want to use Bayesian inference because of the problems I talked about. So what do we do? What you do is, what solves the problems for us is to use an estimating equation, which means the following thing. So what this equation is here is the LT is log number of deaths at week T. The nu of T and beta, these are the parameters we're estimating. So this is what we're trying to solve for. And remember, M is just the cumulative mobility at time T. So this is really just, you recognize this as the residual as if this was a regression model. It's just the observed L minus the model. Then we multiply it by 2 things. There's this WT I'll come back to in a minute, and there's HT. So without getting into too much technical detail, the H's can be chosen to be any functions of the treatment at all, as long as they're not functions of Y. But there's better choices and worse choices of these functions H. Roughly speaking, some H's will give estimators with smaller variances, more efficient estimators. So I'm not going to talk a lot about these H's, the choices down here, but it's not important. They're just given functions. What is important is these weights WT. The weights WT are what makes this causal, that if I didn't have the weights in here, I would just be doing linear regression of Y on A, basically. That's not getting the causal quantity one. But these weights are called propensity scores. So the numerator is the density of treatment at time AS given the past treatments. And in our data, it turns out this is very easy to estimate because mobility in in week 10 is almost completely predicted by mobility in week 9. And then it's basically Markov. It turns out to be Markov. So it's not dependent on the past. It's only dependent on the last value. So this is going to end up being really the density for mobility at week S given the previous week. And that turns out to be very accurate. The denominator is the density of mobility given past mobility and given past deaths. And this also turns out to be, in this particular case, easy to model. But at any rate, you might wonder now, where is this coming from? So why am I putting these weights in here? Why am I using this equation? Well, I don't have time, but there's a theorem that says that if you solve this estimating equation, if you define beta hat in particular to be the solution of this thing with these particular weights, then you are estimating the parameters of the G formula correctly. And in particular, under some conditions, the estimator you get out, unlike the MLE or the Bayes estimator, it is not prone to that null paradox that I talked about. And furthermore, there's, again, I'll leave out the conditions and so on, but beta hat turns out to be asymptotically normal with a standard error that we can estimate and so on. So this is the place where we departed from typical epidemic modeling, where people construct models and then use them to do lots of things, whereas at this point, we sort of throw away the model and just extract this causal piece of information from this G formula, and we estimate it without the model at all, but using an estimating equation. This solving the estimating equation really ends up just being weighted least squares with these weights. Now, the details about how to estimate these weights are it's an interesting thing. It takes some work, and there is a Markov assumption that I talked about. We have a paper about this, which is to appear in the Annals of Applied Statistics, or it's on archive. And if you're interested, you can see we have a whole section talking about how this estimation of the weights is done, but I'll skip that today. And again, there's details about how to choose how many terms were in that polynomial that was used to describe the epidemic when there's no treatment. So at the end of all this, just to back up a bit, we started with an epidemic model. We did the G formula, which gave us essentially what I call a marginal structural law, a model for the causal effect, not for the data. We estimated the parameter beta in that model now using this estimating equation. And now we can put that beta back into the model and answer counterfactual questions. And the way we parameterized it is, if beta is negative, it means staying home reduces deaths, which is sort of, I mean, it would be pretty hard to imagine that, otherwise. This is an example where the sign of the parameter, it wouldn't make sense for this to be positive. And if it is, it means there's something wrong in your model probably. So that's sort of a helpful thing. So we analyzed all 50 states separately. And that's a little bit different also than how this is usually done in the literature. But when you bring the states together, you should really be including lots of confounding variables because the states are so different. And we thought it was cleaner, instead of doing that, to just analyze each state separately, which is obviously less information per state. But we just thought there was less chance of confounding. And, it could have come out that these betas, some were positive and some were negative. It could have come out that some were 10 times bigger than the other one. We were very pleased to see, here are the beta hats for the 50 states with confidence intervals. And on the x-axis, I've sorted the states by their log population. So the big states are to the right. And so we feel that this is very reassuring that they all have roughly the same magnitude, in the range of -5, plus or minus a certain amount. Most of the confidence intervals are completely negative, suggesting that, we can say that it's significant in the, traditional sense that these are significantly smaller than 0. We shouldn't take that too seriously, but the fact that it all came out in that direction is very reassuring. So we can now put this beta back into the model and say, what would have happened? Oh, this is remember I said there's a non-parametric component saying what would have happened without any intervention, the sort of baseline. And the only thing I wanted to point out here is that this is that curve for 4 states. It tends to go up almost linearly and then bend to the right. And that makes perfect sense because we know that the death rate from COVID started to go down after a while because of better treatment, and the most susceptible people had already had it and so on. So that's just another check that this makes intuitive sense. But here's the kind of things we want to look at. So let me just pick New York here, the second one. The black line is the observed mobility pattern. And so when we ask, what would have happened if they had stayed home a week earlier, we're really asking, what if I had shifted the black line a week earlier to make it into the green line? That's our hypothetical intervention. And when we say, how about staying vigilant longer? Well, that would be like saying, what if I change the black line into the red line, which dies off slower? So these different interventions I can plug into the formulas, and this is what you get. So this is our main results here. Let's just start here at the top. This is Tennessee. So we just picked a few states here. And what you're seeing here, the black dots are the actual number of deaths over this period of the epidemic. The blue band is the estimate of what would have happened if they had stopped a week earlier, and that's a 95% confidence band. And the answer is, for Tennessee, not much would have changed. And that's presumably because I don't think they started locking down as well as other states. And we can say the same thing if they had started 2 weeks earlier, but look at the third column. If they had not gone back to work so quickly, if they'd stayed vigilant, then instead of this black dotted lines, the dots, which is the observed, our prediction or counterfactual prediction is that it would have gone up like this and then come down. And it's a very narrow confidence band. On the other hand, New York is the opposite. Here you can see that if they had locked down, this is the second row, and the first column, if they had locked down earlier, you can see there's a big drop in the peak. We would have expected a much smaller peak. But if we go to the third column, we can see that if they had stayed vigilant longer, it wouldn't have mattered much. And that's probably because people in New York did stay vigilant for quite a while. So we have these kinds of curves, of course, for all 50 states. But the interesting thing is you really can see state by state how the different scenarios would have affected those states. It's quite informative. I'm starting to run out of time. I don't want to go all the full hour in case there's questions. So we did a lot of sensitivity analysis on this. I'm going to skip most of it. I'll just mention the last one, which is if there's unobserved confounding, then the weights that I used were not correct. Those weights should have modeled other confounding variables. And one way to check what effect that has is to say, well, what if the weights were off by some factor gamma? So this gamma here is like the error in the weights due to unobserved confounding. So if gamma was like 2, it'd be like saying, suppose there's twice as much confounding that you didn't account for. So people usually look in the range of like gamma's 1.1, 1.2, 1.3. But what we find is we can take gamma, and I'll just skip ahead, all the way up to 3 before you see any noticeable effects. So what this is showing here, these are not confidence intervals now. These are the black dots are the point estimates. And the blue bars are showing you, if I say that gamma is 3, which roughly speaking, you can say is like there's 3 times as much unobserved confounding as there is confounding. That's a lot of unobserved confounding. And you can see what happens is that in the smaller states, we actually do lose significance at that point. So if there's a lot of unobserved confounding, we should be cautious about what we're saying about the small states. The big states, these 4 here on the right, are still very significant. Well, actually, I don't have the confidence interval around it. I shouldn't say that, but at least the point estimate is staying away from 0. And if in the middle states, the story is sort of in between. Some of them are moving towards 0 and some of them are not. So this seems to us also like a pretty good sanity check, that the big states are pretty robust to unobserved confounding, the smaller states, not so much. So let me go to my conclusions. Now, I realize that if you have not dealt with causal inference before, well, some of the things I said here could be potentially quite confusing. The thing about the null paradox and why we need to use an estimating equation instead of maximum likelihood or Bayes. These are, again, it's for people to do this kind of modeling all the time, it's quite familiar, but if you haven't, it can be somewhat confusing. But it is an important point, and it seems that these problems mixing causality with epidemic models doesn't seem to be a well-known thing in the epidemic modeling community. And you'll notice our model in the end was pretty simple. There was only a few parameters in it. In contrast, a lot of the papers we saw during COVID were very complex. I just saw one today with 12 parameters in it, and 5 of those parameters are actually functions. And our experience, we have quite a bit of experience now doing COVID modeling, and I'll just say the data are pretty noisy. They're not high quality, and you should be kind of cautious about building models that are really complicated when you don't have really good data. I think keeping simple models is important. We used weeks, but you could use days and so on. And we did this state by state. One could use counties and things like that. So those are interesting things to explore. And we did a separate analysis again for each time series, but there are people who combine them into one. That's an interesting choice. So we are current work is about combining information between states. We have some more work on the sensitivity analysis that I talked about. We're also working on what are called negative controls, which are things that you know are not affected by the treatment, can help you diagnose and correct for unobserved confounding. And we're just finishing a paper now, which goes into much more depth about this problem of relating epidemic models to causal models. So I'll stop there. Thank you very much for your attention.
Great, thank you for the and any questions? Okay. There is some audio problems, so whenever there is a question, somebody will type. Ready? So you can read the question.
Thanks.
Okay. Yeah, I have a question. My name is from the Causal University. My question is related to the evaluation of the proposed method for the causal inference. As I understand, causal inference is a kind of an unsupervised learning, and hence in the presentation you explained how to interpret data and then into legitimate. But my question is, in this case, I can accept your explanation, but in other areas, how to evaluate the performance of the proposed method? That's my question.
Were you able to hear it?
No.
So he asked how to evaluate your estimate.
Yeah, right. Thank you. Very good question, because causal models are notoriously difficult to validate, actually, because by definition, we're trying to predict something that didn't happen. And so there's some intrinsic difficulties. So we do have, but one thing you can do is sensitivity analysis. So I talked, very briefly about one type of sensitivity analysis, but in the paper, we do lots of different types of sensitivity analysis. So we consider just changing the model, trying different assumptions. So testing certain things about independence. So one thing, it's not really validating the model that so much, I guess it's just model checking. So just checking a lot of the assumptions that go into the model. And so basically looking at diagnostics. I'm not sure you can ever really validate a causal model, although I guess you could, in the sense that you could say, okay, so I'm going to predict, Pennsylvania is about to give a lockdown, give us a prediction now using your model of what will happen. And you could do that, and you could check it against it. The problem is, like in a real situation like this, is everything keeps changing. So at this point, our model probably isn't even accurate anymore. So it's very, very difficult to validate a causal model the way you would validate a prediction model.
Okay.
Wonderful talk, very interesting. So I guess your conclusion is to stay vigilant. Is that the conclusion?
That one I heard, yes. No, so I should be clear about that. We don't make any public health conclusion. Once we sort of got our estimate, now to me, making policy decisions, the statistical part of it's only one part of it, right? So if you were a policymaker, I can tell a policymaker, if you reduce social mobility by 20%, here's the effect that's going to have on the outcome. But of course, the policymaker has to decide how about the, economic costs of doing that and the psychological costs. So I'm not necessarily telling people to stay vigilant. I'm sort of being agnostic about what you should do with this information. We're only trying to provide the information.
Okay, I have another question. So these counterfactual, based on causality, is very dependent on your graphical model. You made particular assumptions in deriving your answer. I'm wondering how sensitive your result is on the model, because I'm looking at this and thinking depth is going to affect your mobility. You have mobility as treatment causing or affecting the depth, but you also have depth affecting mobility, I would think. And so if you had like a different model, I was thinking maybe an H&M model. The state, I guess H&M may not be correct, but you have mobility as change, because you said it was a Markov model. I would tend to agree with that. A particular state, the mobility of a state at a particular time would be dependent on your prior, not way before. And based on your mobility at the current time, that would affect your outcome of the death. But you would have, and of course, there are other confounding factors that would enter and affect the death. But I mean, my question is, if you had a different model, how would your results differ? And how sensitive would your output be, your result be? That's my question.
Yeah, thanks for the question. So first of all, I should have clarified this actually, that the counterfactual approach to causality and the directed graph approach are identical. They're just mathematically isomorphic. So I could have done this all in Perl language with directed graphs and all that stuff. You would get exactly the same expression. So and there's no modeling assumption here in the sense that it's a full model. It's a saturated model. We're assuming everything at time t is affected by everything in the path. So it's a completely forward connected DAG we're using. And it is actually an HMM too, because the infections are unobserved. Those are the unobserved states. So this is actually a hidden Markov model. Actually not Markov necessarily, because in general, we allow the time to go further back. But yeah, this is actually a hidden Markov model. So we're not really making, and we're treating this semi-parametrically, which means we're not making any modeling assumption, except we're assuming that whatever is driving this epidemic, in the end, if I were to compute the causal effect using, you can call it, again, Robin's G formula or Perl's backdoor formula from the DAG, they're the same. We're just assuming it's a simple function of A, or it can be approximated by a simple function of A. Other than that, the entire model is completely unrestricted. So this is close to a non-parametric model. So the only issues about sensitivity are, the major two sensitivity issues is when we estimate that formula, we had to model the weights. And so we did quite a bit of sensitivity analysis on how we modeled the weights that go into the estimating equation. And the other one is sensitivity to unobserved confounding. So that's briefly what I talked about, is that's very important. You're absolutely correct that the A's cause Y's and the Y's cause A's. right? It's a fully connected forward graph. That's why you need the G formula. That's why the causal effect is not given by any parameter in the model. It's given by that entire G formula, is because it has to take into account the fact that the Y's are both causes and effects, and similarly for the A's.
Okay, I think we have to stop now and up. So let's thank again to Professor Wasserman.
And thank you for your wonderful.
Thank you.
Bye. See you later.
Bye.
And, thank you.